But we'd also like to look at the radial probability distribution function for the other S wave functions that we've looked at so far. All right? And let me go over here. And the next one that we're going to look at is for the 2S wave function. All right? So this will be the radial probability distribution function for the 2S wave function. This is versus R. All right? And if I plot it, what I'm going to see is something that looks like this. All right? Lo and behold, the most probable value here of R, RMP, this most probable value, let me get my chalk. All right, I'm going to do it. Okay, the most probable value here, RMP, is actually 6A0. Hey, it is most likely for the electron in a 2s state to be 6 times as far from the nucleus as it is in the 1s state. Right? That's what the radial probability distribution function tells us. So, if you have a hydrogen atom that is in the first excited state, that hydrogen atom, in a sense, is bigger. It's bigger in the sense that it is more likely to find the electron a further distance from the nucleus than it is in the n=1 state. All right? The other interesting thing here about this radial probability distribution is that you can see where the node is, where the radial node is. Right? We talked about the radial node last time. This is R equal to A0. A radial node is the value of R that will make your wave function be equal to 0. So that's the radial node. Now, very important here. This R equals 0. R equals 0 is not a radial node. R equals 0 is never a radial node. This gets students into trouble. So let me emphasize this over and over again. R equals 0 is never a radial node. Okay? This R equals 0 right here is a consequence of our definition of the radial probability, 4 pi r squared psi squared dr. That's not a radial node. Okay.